Today, we are going to be beginning our discussion on rotations. There's a lot of stuff that we can talk about rotating objects and the mechanics and dynamics of rotations. One thing I did earlier this semester is I skipped some stuff. I skipped the end of Chapter 3, Section 4, and I skipped the corresponding examples. We will begin today by jumping all the way back to Chapter 3 and looking at the content of Section 3.4 and those examples. And then we'll jump back forward and go to Chapter 5.4 and look at the examples that you can see there on the screen. Rotation. Let's say that you have a rotating object and it rotates by a certain angle and you want to see how far the outside edge moves. That's talking about this. We've got a rotating object and I want to see how far this point, let's say, moves, like that. So I've got some distance from the center. This end piece is some distance from the center. And this is the center of rotation, of course, because it's rotating around that axis. And I rotate it through a certain number of degrees. So you can see as it goes in that arc, however it's going, that it's going to go through a certain physical distance as it goes around the that not quite semicircle, but that arc right there. We've got equations that can tell us how far that it actually moves. In fact, we just need the one. The angle that it moves in radians is equal to the arc length. That is the physical length that that end point moved. Not just like point A to point B, but the length around the curve that that point moved, divided by the radius of the circle. In other words, the arc length that it moved is equal to the angle that it moved times the radius of the circle. Interestingly, this only works if you are using radians. You have to be using radians for this to work. It is important to remember that one revolution around a circle is equal to 2 pi radians around a circle. So let's do a little thought experiment right here with this equation. Let's say that I start like this and I move all the way around like that. So this point is back to where it began. So looking at that again, it goes all the way around like that. Given that, if it went all the way around once, then theta should equal 2 pi. Theta should equal 2 pi. The radius is, well, whatever it is. It's probably, I don't know, 15 centimeters, whatever. If I want to find the distance that that end point moved, the physical distance that end point moved, I would take 2 pi and I'd multiply both sides by r. And so that would make it that the arc length is equal to theta r after I've multiplied both sides by r. Theta is 2 pi and it's times r, 2 pi r. Oh, wait, okay, that totally makes sense. The distance around this circle, like that, is 2 pi r. Obvious. And that's what we know. That's the circumference of the circle that we just made. It's 2 pi r, going around once like that. That equation is really telling us exactly what we already knew, but it's telling us in a more mathematical way that if you go one full rotation around a circle, that's 2 pi radians, and the distance around that you went is 2 pi r, because that's the circumference. Similarly, angular velocity is this quantity called omega. That funny looking W is called an omega. This is specifically a lowercase omega. Lowercase omega the angular velocity is equal to the linear velocity, the regular velocity, divided by the radius of the circle that you're making. Omega is a quantity measured in radians per second. So let me demonstrate that. I've got this that I built out of my Legos just for you, and I'm going to spin it around, something like that. Well, the end point is moving it around at some speed. The end of this contraption is moving around at some speed. And you can also tell that it's moving through a certain number of radians per second. If you watched this at very high speed, or looking at it in slow-mo, high camera speed, then you would see, you could actually measure how many radians it moves through per second. Say in 1 second it moves like that, I guess. I don't know. Well, that would be, what would that be? 3/2 pi radians to go from there to there, 3/2 pi radians. If it did that in 1 second, it would be 3/2 pi radians per second, which I know is a whole lot of stuff. Just think about, it's often easier to think about with just regular numbers. So if you spin it around, maybe it's going through 3 radians per second. I don't know. But you can see how many radians physically it will move through in 1 second. That is called the angular velocity, because it is the velocity in the amount of angle that you're going through per second. That's what we have here with omega. Measured in radians per second, r is the radius of the circle, or the radius of rotation. And so we also see that 1 revolution per second is equal to 2 pi radians per second. If 1 revolution is equal to 2 pi radians, then 1 revolution per second is 2 pi radians per second. Being able to do simple conversions like that will be very important for this stuff. And likewise, if we have kind of an angular distance, theta, we can have an angular velocity, omega, and we can have an angular acceleration, alpha. Here we have an alpha. Alpha is equal to a over r. The linear acceleration divided by the radius that you are going around that circle. And this works the exact same way. I can take my contraption and I can start it off slow, and then I can speed it up and speed it up and speed it up more and more and more. And so I had to have some angular acceleration. It started off at a very low number of radians that it was going through every second. This is less than 1 radian per second. And then it was going at 1 radian per second or such. And then it was going multiple radians per second. And so its angular velocity had to increase. And if its angular velocity increased, then that meant that it had an angular acceleration. I have a question for you. We don't have time to go over it very well, but question for you. What are the units of alpha, given that the units of theta were radians and the units of omega were radians per second? Can you tell what the units of alpha will be? They've got to be radians per second squared. Yeah. This operates just the same way as distance and velocity and acceleration, or displacement velocity acceleration. Radians is kind of the angular unit of displacement. Radians per second is the angular unit of the equivalent of velocity. Radians per second squared is the angular version of the equivalent to regular acceleration. So there's that same pattern. You have some base unit, and then you have that base unit per second, and then that base unit per second squared. It's like the displacement and then the velocity and then the acceleration of that thing. Same concept. This is all very good news for us. We get to use the exact same equations that we had before with a couple small changes. We had the equation that we all knew and love. Delta x is equal to v naught t plus 1/2 at squared. Well, now we have replaced the x thing with theta, because x is physical distance, theta is angular distance. We replaced velocity, which is like a linear velocity, velocity in a line, with omega, which is the velocity of the angle, the angular velocity, how much angle you're going through per second, times t again. So that implies that this is the initial velocity, the initial angular velocity there, because it takes the same place as the initial velocity in the old kinematics equation. Plus 1/2 times alpha. Alpha replaces a times t squared. Will these have a derivative relationship like the kinematics equations? Yes. These are all related by the exact same kinds of rules, including that the velocity, the angular velocity, is the derivative of the position. The acceleration, the angular acceleration, is the derivative of the angular velocity, etc. And antiderivatives the other way around. That's really, really convenient for us. We've got omega final squared, which used to be v final squared, is equal to omega initial squared, which used to be v initial squared, plus 2 times alpha, which used to be a, times theta, which used to be delta x. Remember, v final squared is equal to v initial squared plus 2a delta x. Well, this is the exact same thing. You just replaced the kinematics, the linear kinematics, with angular kinematics kinds of variables. V final is equal to v initial plus at has been changed to omega final plus omega initial plus alpha t. And then I also give you these equations here that kind of help you relate one thing to another, help you relate the angle to the distance, the angular velocity to the linear velocity, and the angular acceleration to the linear acceleration, as long as you have some radius that you're working with. If we are comfortable with this, then let's do an example. The slide that I had on the screen gives you all this information, but I've written it here as well so that we can go through it more easily, so I don't have to switch back and forth so much. We have a rotating CD. Let's take a CD which goes from rest to rotating at 31.4 radians per second in a time of 0.892 seconds. So it goes from rest to rotating that quickly in that amount of time. The radius of the CD is 0.05 meters or 5 centimeters, but we need to get everything into meters anyway, so it's good that it's already in meters. The first question that I give you is just find the angular acceleration. Now, it is very important that you be able to tell, if I give you alpha, think, oh, that's angular acceleration. If I say angular acceleration, you should be able to say, oh, that's going to be alpha on my equation sheet. That right there is also very important. We need to find alpha, and I give you the equations on the slide, but I'll tell you that if we're going to find alpha, we need to use, well, one of those equations, and I'm going to recommend we use this equation to find alpha. Omega final, do we know that? Yeah, it's this. The CD goes from rest to rotating at that speed in that amount of time. So that must be omega final. Well, that is equal to omega initial. Do we know omega initial? Oh yeah, well, it's rest. Rest means it's not moving. When you're resting, you're not moving. So that is going to be 0 in that case. Plus alpha, oh, we're looking for alpha, well, that works, times t. Well, we've got t right there, 0.892 seconds. Plug and chug. It is literally that simple to use this kind of equation. We plug in our values and we solve for what we need. Nothing more to it than that. That is good news. Next question, just to give you I'm just trying to give you a bunch of different questions to look at to help you get comfortable with this, using this, and seeing that it really is just the same as V final is equal to V initial plus AT. If I gave you a ball goes from rest to moving forward at 31.4 meters per second in that amount of time, and I asked you to find the acceleration, you'd still do the exact same thing. It would be the V final is equal to V initial plus AT equation instead of this one, because if I give you linear stuff, you need a linear equation. But it's the same process. That's what's so nice about this. You don't actually have to learn any new skills to do this. If you learned kinematics, then this should be second nature to you at this point, because this is the exact same thing as kinematics. It's just replacing the variables with other variables. So how far does it rotate in 0.892 seconds? As it's getting up to speed, how far does it physically rotate? The best equation to use for this is the equivalent of the old standby equation. Remember, delta x is equal to v naught t plus 1/2 at squared. It's the same thing. We need to figure out how far it rotates in angle. The actual question on the slide asks for how far it rotates as an angle. And so we're looking for that. Omega is the initial angular velocity, as we can tell, because this equation takes the place of delta x is equal to v naught t. That naught makes it an initial. So that must be the initial velocity of 0, the initial angular velocity of 0, plus 1/2 times alpha. Oh, wait, we already figured out alpha times t. We're given t squared. You plug that in, 0 there because omega initial is 0, 1/2 alpha t squared. That's equal to theta. Theta is 14 radians. It rotated through 14 radians as it got up to speed. Next question, what is the tangential speed at the edge? If I have some rotating object like this, then the speed at the edge you can figure out. And I gave you the equation for that. The angular velocity is equal to the linear velocity divided by the radius of rotation. So if you've got some rotating object like that, you look at the radius, so the point that you want to look at from the center of rotation, look at that radius, and you say, well, you take that radius, you take the angular velocity that it's rotating at, so how many radians per second, you plug it into this equation, you can solve for the linear velocity very quickly. So we already had that, and we can find the velocity. The velocity ends up being just over 1.5 meters per second. So not too bad. Finally, what is the tangential acceleration as it gets up to speed? Tangential acceleration, same kind of thing. We've got alpha, which we have from here, is equal to the tangential acceleration. Tangential means on a tangent, and I'll just draw that here. These things are all rotating in circles, and so a tangent line would be like that. So your tangential acceleration is how fast you're accelerating in that line. Of course, you're going from one direction to, a couple seconds later, you're going in that direction, to a couple seconds later, you're going in that direction. Talk about that a little bit more in not too long. But you just plug in the numbers and you find the acceleration that way. It is exactly as easy as it looks, fortunately. There's not very many things I can say that about, but this is one of them. This is one of the, yeah, it's as easy as it looks, fortunately. And I hope it looks easy. Here's all those questions. You can peruse them at your leisure. I give you the answers again there. and the work again there.